Hello everyone. Today I will discuss about the basic theory behind IR spectroscopy. I have decided to disintegrate this video for better understanding of IR spectroscopy into three parts. So in this part, which is part 1, I will discuss about the IR spectroscopic behavior of diatomic molecule along with the basic concept of it and the theory behind IR spectroscopy. So let's begin. In my previous video, I have discussed broadly about the interaction between electromagnetic radiation and matter, and we know the importance of quantized energy levels of molecular state for the interaction with particular part of electromagnetic spectrum. If we follow the energy level diagram, we find that energy difference within the vibrational energy levels are quite high with respect to rotational energy level. Data do support the fact, which is the vibrational energy level is approximately 3000 centimeter inverse, whereas the energy difference of rotational energy level is 10 centimeter inverse. Thus, definitely the energy required for this transition is greater than microwave and meets with IR region, as the frequency and wavelength of IR spectrum is 430 terahertz to 300 gigahertz and 700 nanometer to 1 millimeter respectively. This IR region can be divided into three parts, but mostly mid-IR region is responsible for functional group dependent vibration modes of bonds. To show IR activity, definitely presence of dipole moment during vibration of bond is an absolute necessity. When I am discussing the IR spectroscopic properties of molecule, definitely vibration of bond is related to it, which defines that bond related to our discussion is definitely a non-rigid bond. That is, the bond length changes. Practically, any bond is actually vibrating about a mean position due to the presence of elasticity. Thus, determination of energy required for vibrating bond is quite important. To keep it simple, I am starting the discussion considering a diatomic molecule. When a diatomic molecule is vibrating along two atoms, two situations can be generated. One is extension, another compression. So, there is always a mean distance present in a diatomic bond, where the repulsion between the positively charged nucleus or negatively charged electron cloud of atoms are balanced by the attraction between the negatively charged electron cloud of one atom and nucleus of another atom, which we know is positively charged, which is known as the R equilibrium. The distance of the bond is known as R equilibrium. Considering spring-like extension and compression in bonds, Hooke's law is followed by a bond as well. That is, F equals to K into R minus R equilibrium. R is the changed position or the position of the bond which is changing with respect to the R equilibrium. K is a constant which is known as force constant, and F is restoration force. Now, this means that restoring force during the extension or compression of bond is proportional to the distortion of the bond with respect to the mean position, but in opposite direction, which is simply if a bond is extended with respect to its equilibrium position, then restoring force will act to compress the bond to its equilibrium position. The concept can be explained using the graph. You can see that AB dash is the shifted or distorted position with respect to R equilibrium. That means the amount of change in the position is B dash from the R equilibrium. So, if the amount of distortion, the amount of change from the R equilibrium position is greater, the amount of restoration force required is also greater. That's why epsilon 1, which denotes the energy, is lesser than epsilon 2, where the restoration force required is more because the distortion from the equilibrium position of B dash is lesser than B double dash. This is the simplest harmonic oscillator model for vibrating diatomic molecule, where the energy is E equals to half K into R minus R equilibrium square, where K is force constant. During discussion of energy of simple harmonic oscillator, we found that vibration frequency of bond is dependent upon mass of the system and force constant, and that oscillation frequency is omega oscillation equals to 1 by 2 pi root over of K by mu in Hertz, where K is the force constant as discussed earlier and mu is reduced mass, which we have already discussed in the microwave spectroscopy. Schrödinger equation for quantized vibrational energy level is EV equals to V plus half H omega oscillation in joules, where V is the vibrational quantum number. The value varies from 0 to 1, 2, 3, etc. If V equals to 0, then we get epsilon V equals to omega oscillation bar by 2 centimeter inverse. This implies for diatomic molecule vibrational energy can never be zero. That is, atoms can never be completely at rest with respect to each other. This is known as zero-point energy. But in case of microwave spectroscopy, we have discovered that at zero rotational quantum number, the energy becomes zero. The selection rule for harmonic oscillator undergoing vibrational changes is del V equals to plus minus 1. Thus, considering the diatomic harmonic oscillator, the energy difference between the corresponding vibrational energy levels is omega oscillation bar centimeter inverse. Thus, amount of energy absorbed by vibrating molecule must be its own oscillation frequency. Along with this, definitely presence of dipole moment is of utmost importance to show vibrational spectra. Thus, only for heteroatomic molecule, only we can see IR spectra. But in case of homoatomic molecule, as the dipole moment is not there, thus we cannot see any IR activity for those molecules. But real molecules do not follow the exact laws of simple harmonic motion. Although elastic, but they don't obey Hooke's law homogeneously. Because if bond between atoms is stretched, then at a certain point it will break and molecule dissociate into atoms. Thus, for smaller compression and extension, bonds may be taken perfectly as elastic, but for larger amplitude, it will show anharmonic behavior. A purely empirical expression which fits the curve showing the anharmonic nature of diatomic bond was derived by P.M. Morse and shown here. In this expression, A is a constant for a particular molecule and D equilibrium is the dissociation energy. Thus, Schrödinger equation for anharmonic diatomic molecule will be different from the harmonic one, which is shown in the slide, and where V is the vibrational quantum number, omega is the rotational frequency for anharmonic oscillator, X is anharmonicity constant, where for stretching a bond vibration, the value is always small and positive. So with increasing V, vibrational levels crowd more closely together with each other. Now comparing the energy levels of harmonic and anharmonic oscillator, we get that anharmonic oscillator behaves like harmonic oscillator with an oscillation frequency decrease, which steadily decreases with the value of V or vibrational quantum number. In a hypothetical situation of V equals to minus half, in that only omega oscillation bar is equals to omega E bar. This shows that at lower V value or lower value for vibrational quantum number, anharmonic oscillator can be comparable with harmonic oscillator. But the zero-point energy for anharmonic oscillator is different from the harmonic oscillator, which is also shown in the slide. The selection rule of anharmonic oscillator differs. In harmonic oscillator, it is only plus minus 1, whereas for anharmonic oscillator, it is found to be plus minus 1, plus minus 2, plus minus 3, etc. The orders of spacing between levels are 10 to the power 3 centimeter inverse that we have already known from our previous discussion. Now the spectral lines from this anharmonic model we can see that for the 0 to 1 transition, that line is known as fundamental absorption. The transition from 0 to 2 level, the line is known as first overtone. The line from 0 to 3 is known as second overtone, and so on. So the energy calculation with respect to the different selection rule is also calculated here and shown in the slide. The case of hot band is when the transition is taking place from V equals to 1 state to V equals to 2 state. The lines produced by this kind of transition is known as hot band, but bit weaker with respect to this kind of fundamental absorptions. For the possibility of this kind of transition, we need to populate the V equals to 1 level. So to make it possible, we need to give heat or energy. So if the molecule is heated or giving some energy, some amount of electrons can be transported to 1. From there, V equals to 1 to V equals to 2 transition is possible. So in those cases, hot bands are observed. As two motions, rotation and vibration, are different, thus a diatomic molecule can execute rotation and vibration quite independently. This approximation is known as Born-Oppenheimer approximation. Thus, the total energy is actually the combination of rotational energy as well as vibrational energy. So, the expression of energy related to the spectra is related to both rotational part and vibrational part, which is shown in the slide. Now, the selection rule for this Born-Oppenheimer approximation is del V equals to plus minus 1, plus minus 2, plus minus 3, etc. and del J equals to plus minus 1. Thus, the equation representing the vibrational rotational spectrum is given in the slide. So, in this expression, we have a term M, and the value of M varies from plus minus 1, plus minus 2, etc. Where the frequency of, in this equation, the frequency omega 0 bar is known as band origin or band center. Since M is not equals to 0, the line at omega 0 bar is absent. So when M value is negative, or let's say del J is minus 1, that part of band is related to P branch. And if M value is plus 1 or negative or positive, that means the J value is del J equals to plus 1, then the branch is known as R branch. So here the lines are described as if del J varies from minus 2, minus 1, 0, plus 1, plus 2, then the corresponding branches observed in the spectrum is known as O, P, Q, R, S respectively. So an interesting thing you can see from the spectra, that in the spectra we can observe and we can always tell that P4 is the line where the intensity is highest. But the Born-Oppenheimer approximation is also not perfect. It has its own limitation. That is, a molecule practically vibrates at 10 to the power 3 times during a single rotation. So during the rotation, the bond length varies, because during the vibration we know bond cannot be static. It cannot act as a rigid rotor. That's why the B value is also changing. The B value is a rotational constant, but which we have not considered in case of Born-Oppenheimer approximation. But in actual case, B value is, as we know that B value is proportional to 1 by R square. So as the bond length is increasing, so the B value is decreasing with respect to vibration, and thus the energy levels are changed. So the corrected terms for this approximation is shown in the slide. So we have to modify the energy difference of rotational as well as vibrational level according to the breakdown of Born-Oppenheimer approximation. Then only we can get the perfect calculation for the spectra. So in this video, I have discussed about the basic idea of IR spectroscopy, which is based on the diatomic molecular model. So this diatomic molecule, I have used both the harmonic as well as anharmonic model to determine the vibrational spectra for any kind of diatomic molecule. In my next video, I'll discuss about the IR spectroscopy for polyatomic molecular system. Till then, bye.